afternoon. We are going to take notes on section 6.4, which is ways to prove quadrilaterals are parallelograms. One thing that you're going to notice in this section is that many of the theorems we've been learning about parallelograms actually work to prove figures are parallelograms. And then there's a few other ones that we sneak in there. So let's go ahead. Roman numeral 1, to prove a quadrilateral is a parallelogram by the definition. And it's by the definition of a parallelogram. So here it goes. If both pairs of opposite sides of a quadrilateral are parallel, then by definition the quadrilateral is a parallelogram. I want to draw your attention to one part of this, which is that the if includes it being a quadrilateral, a four-sided figure. It has to be a four-sided figure or none of these will work. All right, so illustrating this, if both pairs of a parallelogram, of a quadrilateral has both pairs of opposite sides parallel, then it is a parallelogram. So if AB parallel to DC and AD parallel to BC, then you have a parallelogram. And from there, you can use all of your nifty theorems that we learned in the last section. That's by definition. That's how you prove it's a parallelogram, by the definition. Okay, Roman numeral 2. Theorems that prove quadrilaterals are parallelograms. Everything in here starts out given a quadrilateral. So given a four-sided polygon. So it has to be a polygon. It has to be four-sided. If both pairs of opposite sides are congruent, then it is a parallelogram. So if AD and BC are congruent, AB and DC are congruent, notice they don't have to be congruent to each other, then we have a parallelogram, which means left and right sides are parallel, top and bottom sides are parallel, because that is the definition of a parallelogram. Okay, flip the page. All right, Theorem 615 starts out, given a quadrilateral, if one pair of opposite sides are both, so there's two things that have to be true, are both congruent and parallel, then it is a parallelogram. So this one's kind of different because most of our other theorems deal with both pairs of opposite sides, whereas this one only deals with one pair. So if AB is parallel to DC and AB is also congruent to DC, then you can prove it's a parallelogram. And of course, that means opposite sides are parallel. So notice this is only one pair of sides. Evidently, it doesn't matter what the other two are doing. Okay, Theorem 613, given a quadrilateral, if both pairs of opposite angles are congruent, then it is a parallelogram. Okay, so if A is congruent to C and D is congruent to B, notice you have two obtuse, two acute, then the whole thing is a parallelogram, which means left and right sides are parallel, top and bottom sides are parallel, and we get all of our good theorems. Okay, D. Theorem 614, given a quadrilateral, if the diagonals bisect each other, then it is a parallelogram. So this one's kind of interesting because it doesn't matter that the diagonals are different lengths. So let's draw a diagonal from AC and DB. So you've got your diagonals. So A to the center point to C are the same, and DB is broken into two pieces. Notice there's two shorts and two longs. If the diagonals bisect, then you have a parallelogram, which means left and right sides are parallel, top and bottom sides are parallel. All right, flip the page. Theorem 612. Given a quadrilateral, if an angle is supplementary, which means adds up to 180, if an angle is supplementary to both of its consecutive angles, then it is a parallelogram. Okay, so let's say that we have angle A, and B is one of the consecutive angles, and they're supplementary. So A plus B equals 180 degrees. The other consecutive angle is D, and A plus D is also 180 degrees. So A is supplementary to both consecutive angles. If that is the case, then you have a parallelogram. And again, that means left and right sides are parallel, top and bottom sides are parallel. Okay, we're going to do some practice, and I want to help you strategize how to do these always, sometimes, or never questions, which most students find quite challenging in this section. Okay, so let's look at the first one. The diagonals of a quadrilateral, and again, a quadrilateral just means it's a four-sided figure, blank, bisect each other. Okay, so you've got to think of all the types of quadrilaterals that we can list. So we have parallelograms, we have trapezoids, we have kites, we have rectangles, we have squares, and of course we have rhombuses. So all of those are four-sided figures. So do all of them have diagonals that bisect? Do some of them have diagonals that bisect? Do none of them have diagonals that bisect? So for a parallelogram, yes, they bisect. For a trapezoid, yes, they bisect if it's isosceles. Now, for a kite, it does not bisect. You've got a short and a long piece. It bisects one pair, but not both pairs. So we have some that are yes, one that is no. We don't need to consider anything else. This is a sometimes question. So by making a short list and then going through each item, you're more likely to figure out which ones it applies to and which ones it doesn't. Okay, number 2. If the measures of two angles of a quadrilateral are equal, then the quadrilateral is blank a parallelogram. So it doesn't say which two angles. It just says the measures of two angles. So it could be 2 or it could be 4. So the question is it always a parallelogram? Is it sometimes a parallelogram? Is it never a parallelogram? Well, obviously in a parallelogram, we've got opposite angles congruent, so that's a yes. In a trapezoid, especially an isosceles trapezoid, there are angles that are the same. But in a trapezoid that's not isosceles, maybe something like that, it could be the same, but it isn't necessarily the same. So these are yeses, and this is a no, so we have sometimes. The other shape that leaps to mind for this is a kite. In a kite, there are only two that are the same. So that would be a yes. But because some trapezoids do not, that's we get the sometimes. Okay, number 3. If one pair of opposite sides of a quadrilateral, so one pair of opposite sides, this is only one pair, that's important, and its opposite sides are congruent and parallel, then the quadrilateral is blank a parallelogram. Well, we actually have a theorem that says if one pair of opposite sides is congruent and parallel, you have a parallelogram. So because this is a theorem, it's going to be always. If you can name a theorem, it's always. Okay, number 4. If both, so this is both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral blank is a parallelogram. Well, again, we have a theorem for that. The theorem says if both pairs of opposite sides are congruent, you have a parallelogram. So this is an always because we have a theorem to back it up. And number 5, to prove a quadrilateral is a parallelogram, it is blank enough to show that one pair of opposite sides is parallel. So the question is there any theorem that says that one pair of opposite sides has parallel and nothing else? Well, there isn't. One pair can be parallel and congruent, or two pairs parallel, but just one pair being parallel is not enough information. So that one would be a never. Okay, part B. This is the bulk of your homework, which is stating your theorems. It says state the principal definition or theorem that enables you to deduce from the information given that the quadrilateral ABCD is a parallelogram. Okay, so the information you're given is that BE equals ED, CE equals EA. So what is the theorem? It says if the diagonals of a, and I'm just going to put quad for quadrilateral, if the diagonals of a quadrilateral bisect, then it is a parallelogram. So all we have to do is state the theorem, write the theorem. Okay, number 2, we'll use the same drawing here. BC parallel to AD, BC congruent to AD. So the same pair is parallel and congruent. So here's our theorem. If one pair of opposite sides of a quadrilateral, I'm going to put quad, of a quad, are parallel and congruent, then it is a parallelogram. So a lot of these are stating the theorems many, many times so that you commit them to memory. That way when you need a theorem on an SAT or an ACT or a graduation test, that you're able to bring them to mind because you don't have notes on those tests. And they are high stakes testing for getting into college, graduating from high school, and getting scholarships. So we do want to commit these to memory as much as possible so that we have them in our math library to use when needed. That's everything for today. Have a good afternoon.